In this chapter, we're going to be looking at the limits of sequences. In this lesson, we're going to be providing some background material.
Hi, everyone. So in this series of videos here, we're going to be looking at sequences and series and limits, okay? And specifically in this next kind of immediate series of videos, we're going to be looking at the limits of sequences. Now, let's talk about this. So why bother? Why is this important here? So what I'm going to do is I'm just going to kind of take you through some of the ideas here real quick here, but what we're going to try to do here is we're going to move from this topic into calculus. And calculus is the math, like it says here, is the math of the world in motion, okay? It's how one variable affects another as it changes. Now, and that can be sometimes hard, sometimes easy. It kind of depends on you. Some of these concepts are quite challenging, but others are actually fairly obvious when you just sit back and think about it for a bit here. Now, when Newton first envisioned calculus, he had to use something that he called an infinitesimal. Okay, and those were required to make his calculations work. Now, here's the issue with it, that the concept was not obvious. Okay, it was not 100% clear. And so, like it says here, it was a value that was essentially zero, but not zero. It was so close to zero that you could treat it as if it was a zero, as long as you kept in mind that it wasn't zero. And like the question asks there, is that confusing? Well, yeah. And it took a while before that ambiguous concept of an infinitesimal here was replaced with something that had a lot more of a solid foundation to it, called a limit. And that's what we're building towards here. And so what we want to do here is we're going to use this idea of sequences and series, something that students will be quite familiar with because of their exposure to those concepts in high school. So we want to give you guys a really good foundation for this concept of a limit so that we can transition from there to applying it to the kind of the foundations of calculus. And our goal here is to provide not just an understanding of the kind of the basics of calculus, but to give you a more like a deep, more rigorous understanding. So what you might ask at this point right here is, well, what do you got to know before we begin? And that's actually what we're going to take a look at right now. We're going to take a look at some of the definitions and whatnot that we'll need moving forward. Okay, so to begin, we're going to talk about some notation and some vocabulary here. Because like it says up here, one of the biggest barriers that people have in really appreciating and progressing through mathematics is they get intimidated by the symbols and whatnot that mathematicians use. But the symbols are typically used to make things clear and for the sake of efficiency and communication. But you have to know what they are. You have to know what they represent here. And oftentimes, they're used to represent some very basic ideas. What we need to do is make you familiar with those symbols so that you can access those ideas that they're representing. Okay? So to start off with, we're going to take a look at interval notation. So what we're seeing on the left-hand side of the arrows here, these are ways of writing the exact same relationship on the right here. So A, when we write it like this, with the parentheses A, comma B, close parentheses here, that is the same as saying that X is going to be some value greater than A and less than B, okay, not including the endpoints. And as soon as we use square brackets here, we mean that to include those endpoints. So from A, so X is greater than or equal to A, and X is less than or equal to B. And then we can do kind of half and half here. We can have one end where it approaches but doesn't include, and the other one that does include. So what are the other things that we include here, that we say here, we would call this an open interval. And right here, this is a closed interval. Okay, and then these other two here, these are going to be half open, half closed. Sometimes you're going to hear these referred to as soft brackets. And these ones here are Okay, these ones here are hard brackets. Okay, it's just some stuff to be aware of. And then we're talking about number sets. This comes up an awful lot. And again, you're probably familiar with these, but it's not a bad idea to review some of them. The n, these are your natural numbers. Okay, 1, 2, 3, and so on, the counting numbers. Z refers to the integers. Okay, the positive and negative natural numbers there. Okay, with 0 included. Okay, Q are rationals, so they are numbers that are represented as that in that division form there, where A and B are both integers. Q with the bar over top are numbers that are not rationals. Okay, so these would be your non-terminating, okay, non-terminating, non-repeating decimals. Oops. And then the real numbers, the R here is the union of the rational and the irrational sets there. Together, those are all those real numbers there. Okay, so like it says here, with that being said, whoops, we can now move forward with a more conceptual foundation of this chapter here. So the following ideas are going to be important that we'll be using in the development of the concept of the limit. We're going to use those things here. So just to introduce some of the next ideas here, we're going to introduce two slips. Oh, I forgot to switch back over. We're going to introduce two sets here, A and B. So A is going to represent the set of numbers 3, 6, 2, and 4. And B is going to represent the set of all x values where x is somewhere along that interval. And we just introduced the interval notation here. It's going to be somewhere along the number line here from -2 to 2. And maybe we think of it like this, where we include the 2, but not the -2, and it's going to be all values in between here. So that's what we're looking at right there. All the numbers that would be represented by that here. Okay, so now to start this off here, we're going to introduce a couple of new ideas. We're going to introduce upper and lower bounds. So the upper bound of a set S is going to be a number m, okay, such that if S is in S, so when we're going to use lowercase s to represent an individual element of the larger set S, okay, and if S is less than or equal to that number m, then a lower bound of the set S is a number p, such that if S is an element of S, then S is greater than or equal to P. Okay, so I hope that makes sense here. So the upper bound is going to be some number m, such that if S is in capital S, if it's in the set, then that element there is going to be smaller than m, and a lower bound is going to be some number such that if S is in that set S, it's going to be larger than or equal to P. So, and like it says here, we don't want to get lost in the symbols here. The word bound is being used as you might expect it. It's a boundary, okay? In fact, that might even be a better way of putting that there. It's a boundary. It's like a fence at either end of the set. The number m doesn't even have to be part of the set, okay? And in fact, based on the above definition, it can be any particular larger value than that set. Okay, so now we're going to take a look at a couple of questions dealing with those sets A and B that we just introduced a moment ago. So the question here says, okay, watch this. So we want to identify the lower and upper bounds for the set A defined above. Okay, so we're going to take a look at that set here. And I noticed that the largest value, okay, the largest value here is 6. So my upper bound, okay, therefore my upper bound is going to be any number that's greater than or equal to 6. So I could choose, 7. If I pick any particular value out of that set, it's going to be less than 7. Okay? Just like the smallest value, okay, my smallest value is, 2. Therefore, my lower bound, okay, the lower boundary to this particular set here, and we called it P before, it could be any number less than or equal to 2. So like, I mean, it could be anything. It could be like -1. Okay. So as long as these numbers are greater than or equal to the largest value or less than or equal to the smallest value, those work. So now I tell you what, let's take a look at the next question here. It says, identify the lower and upper bounds for the set B above. Now I tell you what, maybe pause the video right now and answer that question, come up with an answer. So when we take a quick look at this, the largest value, okay, is 2. And again, that is included in the set here. So we can choose any number, okay, greater than or equal to 2 here. So I don't know, let's say maybe in this case here, we say 2, because it could be it's that or equal to that allows me to do that. Okay, and then the smallest value is, well, actually, I don't know what the smallest value is in that set. Isn't that interesting? Okay, I don't know what it is. It gets closer and closer to -2, but bear in mind, -2 is not included in that. So what is the next real number that's bigger than -2? I don't know. I don't know. But I know that if I choose any value from -2 or below, any number that I do pick in there is necessarily going to be larger than it. Okay, I don't even have the option in this case for or equal to, but I know for sure that any number I pick in the set is going to be larger than that lower bound if I choose any number for P that's -2 or smaller. So like I might choose, for example, -2. I know that any number that I pick in there is going to be larger than -2 because -2 is not included in that set there. But it could have been anything, okay? I could very easily just erase this right now, and we could choose a smaller number. We could have chosen, for example, 0, and that would have worked as well. So now let's take a look at the Archimedean property. Okay, so the Archimedean property can basically be summed up by saying that the natural numbers have no upper bound. There is no largest, okay, natural number. But that's not exactly useful to us in that form here. Another way of stating it, and like they have written here, is that if you've got any two positive real numbers, okay, real numbers, A and B, where A is less than B, then there is always a natural number n, such that if you multiply A by n, you'll get a value that's bigger than B. Okay, so maybe that doesn't make sense immediately. Let's take a look at an example here. Okay, so let's take a look at the question here. It says, find a value of n such that A times n is greater than B if the values of A and B are 0.02 and 738 respectively. Okay, so what we're saying here is, okay, we are looking for A times n to be greater than B, particularly if we use the specific values 0.02n and 738. Well, we can determine what that is by simply dividing both sides by that coefficient, right? That 0.02, just like you would if this was an equality here. Yeah, people, if you've studied inequalities before, you've done this as well. So this is going to be n is greater than 738 divided by 0.02. And when we do that, we are going to get that n is going to be greater than 36,900. So as long as you pick a natural number larger than 36,900, then A times n is going to be larger than B. Now, just so you understand here, the point of this, okay, the point of this exercise is not finding n. Okay, the point here is that the point is that you can always do that. Okay, that's the issue. So just as an aside, it's worth noting that the Archimedean property amounts to saying that the natural numbers have no upper bound. Okay, so that's, again, another way of stating that. And then again, to reiterate this, the point is not that, hey, yay, we found that number n, but the point is that you can always find that number n to help you do that. Okay, let's take a look at a couple more definitions. Okay, so the next word that we want to look at, the next definition we want to get it. Whoa, way too big. Sorry, I'm going to do that again here. I'm just going to change the size of the pen there. The supremum. The supremum of a set, and it's denoted SUP of the set S, is the least upper bound of the set. Okay, which probably doesn't make a lot of sense right off the bat here. But if P is equal to that supremum of the set, and M is the upper bound for this set. Now remember, upper bound can kind of be any value that's larger than all of the values in that set there, greater than or equal to all of the values in the set. Then what we know here is that P is going to be the smallest value of M, okay, for all possible values of M. P is the smallest one. So in other words, the supremum is that upper bound that's closest, as close as possible to the set here. On the other hand, the infimum, and we denote that INF of the set S, is the greatest lower bound. And so in its definition and its proof here is it's parallel to the supremum here. We're just looking at it from a different direction here. So it helps to have a kind of a different look at this. So as before, like we said before, we don't want to get too caught up in the notation here. And the terminology. We want this to be as clear as possible. We're creating fences. Okay, we're creating fences to enclose a certain set here. So if you take a look at the picture down below here, we've got lower bounds and we've got upper bounds. And so I've put these little red markers there. For example, let's look at the upper bound first. I put these little red markers here to represent all sorts of upper bounds here. In fact, this one here would also be a red one. But okay, of all those fences here, the one that's the smallest upper bound is the one that I've pointed to and labeled the supremum of the set. Okay, there is no value greater than that value. There is no value smaller than that value that represents an upper bound for that set. Just like over on the other hand here, we've got a bunch of lower bounds listed out, but that green one there is the largest of the lower bounds. Okay, so I hope that makes sense. Once it does, once you kind of get your head wrapped around what's going on here, it's actually quite obvious here. But it does help to look at an example here. So let's take a quick look at a couple of examples before we move on. Okay, so what are the supremum and infimum of set A? Okay, so the supremum of A. What is that going to be here? Well, the largest value of set A is 6. And so as a result, we can say that the supremum of set A is going to be 6. Okay, it's not the only upper bound, but I could have used 7, 8, 10, a million, but 6 is also part of the set. It's the largest value, right? So this is the maximum, this is the maximum value of A. Now, on the other hand, let's take a look at the infimum of A. So in this particular case here, notice that the smallest value of set A is 2. That's one of an infinite number of lower bounds to the set, but it is the largest one. Okay, because other lower bounds could have been 1, 0, negative pi, negative 100, whatever. But the largest of those is going to be 2, and that's actually going to make that the minimum value of A. So, I mean, it's pretty easy to identify the supremum and the infimum, okay, if the set has a very clear, obvious maximum value or a minimum value. Now, I tell you what, take a moment here, and I want you to try to find the supremum and infimum of set B. So you might want to pause the video and have a quick look at that. So let's take a look at the supremum of set B here. Now, in this case here, once again, it's pretty obvious what that's got to be because set B has an obvious maximum value, okay? The max value is 2. Okay, and 2 is part of the set. Now, on the other hand, though, Let's take a look at the low bound of the set here. Okay, -2, though, is not part of the set. So I'm taking a look at this right here, and I've got that -2. It's not part of the set. But no matter what value we choose in the set, we're always going to be able to choose another value that's in between it and -2. So like if you think, well, I'm going to choose a value in the set, maybe -1.9. Well, I can find a number in between -1.9 and -2 that's even smaller than that. And every time I do that, I can always find another number in there. So that makes -2 a low bound to the set. Every number in the set is going to be larger than -2. Now, but not equal to, because -2 is not part of the set. Okay, so what we've got here is the infimum of set B is going to be -2. Okay, there are other lower bounds. I could have chosen -3, -5, -100. Those are all low bounds, but -2 is going to be the largest of all those ones, but it's not in the set. Okay, not in the set. So therefore, there is no minimum value in set B. So that's really interesting here, okay? So if the supremum or the infimum are parts of the set is going to have a very clear maximum or minimum value. If the infimum or the supremum is not part of the set, then there is no clear maximum or minimum value for that set. Okay, let's take a look at one more example here. Okay, so for this question here, it says, consider the set defined as, okay, so we're going to have a bunch of these little Sn values, and they're going to be defined as 1 minus 1 over n. So whatever the subscript is of the little s there, that's going to be in the denominator in that term there. So the question is it clear that the supremum of this set is 1? Well, maybe not right off the bat here. It helps, though, to have a look at it, to see it. And so notice that down here, actually it says, this should be n here, and this is going to be Sn. And remember that in this case right here, n is going to be an element of the natural numbers here. So our first number here, the first value of n is going to be 1. Okay, first term 1. And if you plug 1 in, you get 1 minus 1 over 1, which is just going to be 0. And that's what we're seeing right there. So that's n is equal to 1. If n is equal to 2, we get 1 minus 1 over 2. And that's going to be a half, and that's what we're getting here. And then if n is equal to 3, that's going to be 1 minus 1 over 3, and that's going to be 2/3, which puts us right there, and so on and so forth. Okay, every time I do that, the value of that fractional part there is going to get smaller and smaller. Remember, as the denominator gets larger, that value gets smaller and smaller. So I'm starting at 1, and I keep subtracting a smaller and smaller and smaller value as the value of n gets larger. Okay, now, so notice that all the values of the set of S values are less than the value of 1. We're always going to be subtracting. Every time we come up with a term, we're going to be subtracting something from 1. And it's never going to be 0. 1 over n will never equal 0 here. If we try to assign an upper bound to the set that is less than 1, we run into a bit of a problem. So have a quick look here. If we assume, like it says here, if we assume that the existence of a value q such that all of those values of the set are less than q, and q is less than 1, strictly speaking less than 1, okay, so we're not including the or equal there, then it must be true that 1 minus 1 over n is less than or equal to q. Okay? So at this point here, you might be kind of recognizing, we've kind of talked about something that looks a little bit like this before. Like, wasn't that the Archimedean property? Yeah, that's going to come up here in just a moment. So notice that we can rewrite this inequality to get, so we've got 1 minus 1 over n is less than or equal to q. Okay, so I can swap the 1 over n and the q there to get 1 minus q is less than or equal to 1 over n. And then because we know that we're dealing with positive values here, okay, I can swap the 1 over q and the n. And so, and this has to be true for all n, okay? We know, however, by the Archimedean property of natural numbers that since q is finite, there will always exist an n that is in fact larger than 1 over 1 minus q. Okay, has to be. That's the Archimedean property guarantees it. So no matter what value of Q I choose, no matter how close I choose to get it to 1, okay, there will always be a value of n that will be larger than that. Okay, so since we've run into a contradiction here, we can assume that the assumption of the existence of Q is false. And so as a result, we then conclude that the supremum of that sequence of numbers there is actually going to be 1.